Now that we have the law of mass action, let's talk about two typical ways how it's used. I call that equilibrium calculations. There's more ways, of course, how to use it, but those are the two most typical ways. And what is typically given is you are given the reaction, right? Without a reaction, we can't even write down the law of mass action, and we are given the initial concentration for all our reactants. We are running the reaction. We are setting it up. That's the typical situation. I mean, mathematically you could play around in a different way, but that would be atypical. And then there's two typical questions one could ask you, or that are typically raised. One is you measure one of the equilibrium concentrations, say in the lab, and lab 6 of 124, the 124 lab here, actually does that. And then you can compute all the other equilibrium concentrations and the equilibrium constant K. And actually you don't need to compute the other equilibrium concentrations. You can sort of compute them indirectly and then compute the K. The other thing is you already know the K because it has been cataloged somewhere. You can look up what the K is in a table, and it has been cataloged for an awful lot of reactions. And then you can, given my reaction mixture, I can compute what to expect in equilibrium. So you can predict the future strictly, right? If I set up this equilibrium mixture, this will happen with it. Those are the two typical types. And the main tool we'll use for that is the so-called ICE table. Some people like to call it RICE table because it has really 4 rows. And the first row is the reaction, which would make an R in front of here. And then the second is the initial concentration, which makes the I. Then there comes a change, which is a C, and then there comes an E, which will be equilibrium concentration down here. So the first row is always the reaction. Don't forget that. Always write down the reaction and the balanced reaction at that point, right? The balanced reaction is critical. And then the next line, the next row, is the initial concentrations. And you know those are given in both type 1 and type 2 problems. So, you know, I put in concrete numbers here, and I put in a concrete reaction, a toy reaction really. This is a very simple reaction. Just N2O4 is in equilibrium with 2NO2, and we choose this particularly simple reaction because then all the calculations are very simple. And okay, here's my initial reaction, my initial concentrations, and I picked simple numbers, 0.1 mole per liters and nothing. And then I have to make something, I have to do something, and that is a bit of a line you have to get used to. And that's, I have to say, okay, now that changes on the way to the equilibrium concentrations. And I don't know that change, right? But there's no way I know what that is at the moment. I need to compute that. And because I need to compute that change, I give it a name like X, right? It's an unknown, so any unknown is called X. It's a good name for an unknown. Not any unknown, but it's a good name for an unknown, a good enough name. And the question is just, should I use minus X or plus X? And now the book tells you a very complicated way to say, oh, you have to use negative X. And that is simply not true. Negative X is more convenient, right? Because this concentration, if you look at this, if you just look at it, it is very obvious because this is 0 and this is something. This will go down and this will go up to reach an equilibrium. It must be the case, right? This cannot go up and this cannot go down because there are no negative concentrations, which is actually something to keep in mind, right? There cannot be any negative concentrations under any circumstances. That's just that is impossible. So if you get negative concentrations, something is definitely wrong. So this change must be negative. This must go down. But nobody says x must be a positive number, right? I mean, it's convenient to say x is a positive number, but I could choose x to be a negative number. So if I write simply down x will turn out to be a negative number, which is perfectly fine too. So it doesn't really matter whether you write down negative x or x. If I write down negative x will turn out to be a positive number. If I write down x, the math will look a little bit different, but x will turn out to be a negative number, but the absolute values of these two will turn out to be exactly the same. So you get exactly the same result in the end. It doesn't matter. You can do what you want, really. And I know you don't like this. You like something like a fixed recipe, but that's the way of the world, right? There's always more than one way to skin a cat. Okay, let's choose what the book does. The book does negative x, and if this goes down by one molecule, by how many molecules does this go up? Well, there's a 2 in front of here, right? So if one molecule of this sort of breaks up, I get 2 NO2 molecules. So if this goes down by one molecule, this goes up by 2 molecules. Or if this goes down by 1 mole, this goes down up by 2 moles. And we had the same argument when we talked about reaction rates. Those are related by 1 to 2. There's a ratio between the two. And the ratio is you can directly read it off as the reaction coefficients. Here's a reaction coefficient of 1, here's a reaction coefficient of 2, so the ratio should be 1 to 2. So if we choose 1x here, we need to choose 2x there. And that's just the ratio between the coefficients. Okay, and so it's easiest to just copy the coefficients down, right? So as long as you just put in front of your x's all the coefficients you have anyway in the reaction, then you have the same ratios and you can't make a mistake. So that's the easiest way of doing that. Just as a rule, whatever the coefficient is of the chemical, put that in front of the x and you're fine. Now, the other thing is, if this goes down, this goes up, right? So what you have to have on the reactant side, if you have negatives on the reactant sides, you need positives on the product sides, and vice versa. If you have positives on the reactant sides, you need negatives on the reactant sides. You have to make this choice, right? Negative on the left, then you have positive on the right, or vice versa. One of the two. Okay, completed that one. Which means I can now compute my final concentration, and that's a piece of cake because I just have to sum up the initial plus the change. Initial plus the change is negative x, initial plus negative x is that. And then here initial is 0 plus the x plus the change, 0 plus 2x is 2x. So I have my final concentrations now. Of course I don't know them because I don't know x, but at least I know them in terms of x. and I replaced 2 unknowns by 1 unknown. That's the miracle of the ice table, right? Before, I kind of had the unknown final concentration of this and the unknown final concentration of that. And that seemed like 2 unknowns. But it's actually not 2 unknowns. There's just 1 unknown, the x. And that's because of stoichiometry. So how does that look for a type 1 and how does that look for a type 2? We shall discuss that.